want me to tell you when it's in minutes. Okay, so welcome everyone to the last Rencontres of the year. So we are very happy to have Federico Bonetti telling us about symmetry TFTs from string theory. So please, Federico, welcome.
Thank you. Thank you very much for the invitation and for giving me the opportunity of telling you something today about some recent work in collaboration with Fabio, Iñaki, Sagar, and Sakura that has appeared recently. I would like to start with some kind of general introduction and motivation. As we probably all have seen in our scientific lives, quantum field theory is really a powerful and very flexible language. It's not clearly one specific model, but rather a whole framework that has been extremely successful in describing all different kinds of physical phenomena at very different energy scales in very different contexts, from particle physics to condensed matter to the early universe. And among the many tools that theoretically we have at our disposal to try to understand better QFTs, global symmetries play a central role. We know that they are extremely powerful in helping us understanding better these objects. For example, they organize the spectrum of operators that we have in our theory. Moreover, they constrain, for instance, say the correlation functions of such operators that have to satisfy suitable word identities. In many instances, global symmetries exhibit 't anomalies. So they're preserved at the quantum level, but they're, so to say, broken by quantum effects. Even though broken is a misnomer, because as you probably all know very well, a symmetry that exhibits a 't anomaly is not a bad symmetry in any sense. It's actually a feature of the symmetry that we can use to learn more about the field theory. So all of these considerations date back, of course, a long time ago. What has been somehow revisited in more recent years is a vast generalization of what we should mean by the global symmetry. And in particular, the picture that has emerged over the past few years seems to hint that a fruitful way to think about the global symmetries of a given QFT is, in a sense, to think of them as a topological subsector of sorts. This is supposed to be more like to be taken with a grain of salt, but like I think it's a nice paradigm to keep in mind. And one of the reasons why I think it's a nice paradigm is that because if we start thinking about global symmetries this way, a whole lot of new possibilities open up, and we can describe all the ordinary global symmetries that we know and love together with all sorts of interesting generalizations that has promised to be already quite interesting and about which probably we have to learn a lot more. So let me sort of give you a very brief idea of how and why we should think of them topologically. Let's pick a familiar example. Let's say we have a QFT that has an ordinary continuous U1 global symmetry. As we know from standard QFT textbooks, there is a conserved Noether current. And now the idea is to think not about the current, but rather about this operator U that we can construct by integrating the Hodge dual of the current on a codimension 1 manifold in space-time. And here, the main, it's a rather simple observation, but it's sort of quite powerful conceptually. This operator is now topological. If we wiggle a little bit this support, sigma b minus 1, the operator doesn't change simply and exactly because of the conservation equation. So we should think of current conservation as being a topological property. Another thing that it's natural to do in this language is say surround a local operator by one of these U operators. And since U is topological, we can imagine shrinking it. And this operation actually corresponds to the action of the global symmetry on the local operators of the theory. So that brings us from O to O prime. And another important point in this example is that since these operators are topological, we can imagine, say, taking two of them associated to some group elements, say G1, G2, and bringing them together. That should be allowed. Everything's topological. And what we know that indicates to happen is that then we get another one of these operators, and it is associated to the product of the group elements. So in other words, these operators are topological and satisfy a group-like fusion rule. And now the idea is, let's essentially forget about the current, and let's just keep the pictures, the topological perspective, because then we can do all sorts of new things. We can consider higher codimensional U operators. Now they're still topological, but they don't link to point operators anymore, but rather to extended objects, this curly O of NP, and therefore describe what is usually referred to as a higher form symmetry. So an ordinary symmetry is a zero form symmetry and acts on local operators. A one form symmetry will act on lines, and so on and so forth. And also another recent development, which though won't play a big role in the rest of the talk, but I'd like to mention, we can also allow generalization in the fusion rules. For instance, allowing more than one term on the right-hand side. And these have been studied quite intensively recently, and they usually go by the name of non-invertible symmetries or categorical symmetry. Categorical in that group theory is not quite enough to capture what's happening in this fusion, but one can use category theory to formalize a bit better this kind of phenomenon. And why should we care about these generalized symmetries? One of the reasons why they are interesting is that they share many of the useful features of ordinary ones. For instance, they can be spontaneously broken. And I would like just here to remind you of the standard example about one-form symmetries, whose spontaneous breaking or not is actually the same as the familiar diagnostic tool of confinement in terms of Wilson line in gauge theory, if they have perimeter law or an area law. Just like ordinary symmetries, sometimes they suffer from 't anomalies, sometimes they don't. If they don't, we can gauge them, oftentimes recovering new global symmetries. If they do have 't anomalies, those have to match across RG flows. And therefore, we have a lot of constraints on the phases of QFT. This has been applied in many different contexts, even some non-supersymmetric examples in 4 dimensions, and many, many more considerations of this kind. And there is also another application which is slightly more technical, but plays a role in what I'm going to discuss later. So I would like to spend some time reviewing it. And namely that if we think of generalized global symmetries, and more specifically higher form symmetries, they can be very useful in clarifying some subtle aspects in gauge theory. And in particular, what I have in mind is that sometimes it happens that two different gauge theories share the same Lie algebra. So if we look at local operators, they're essentially indistinguishable, but nonetheless, they have a different spectrum of extended operators, for instance, line operators, which makes them different theories with different physical properties. This is something that has been studied first by Gayotto Mornait, and then more systematically by Haroni, Cyber, and Tachikawa. And for example, if we take for the gauge theory with gauge algebra SU2, it turns out that it comes in 3 different varieties that differ on the form of the global form of the gauge group. Is it SU2 or is it SO3? And actually, in the case of SO3, there are 2 different variants that are distinguished by a discrete theta angle. All these details are just an example and not super important. The take-home message is that these are different gauge theories because they have different lines. They can be Wilson lines, Toth lines, or Dionic lines. That's a gauge theory language that I'm using. But there's an equivalent language that states that these theories are different because they have different global one-form symmetries. So there can be an electric one, a magnetic one, or a Dionic one. And this rephrasing in terms of global symmetries, I think it's useful for various reasons. One reason, for instance, is that we can use the notion of gauging a global one-form symmetry to go from one of these theories to others, for instance, from the SU2 to the SO3+. And maybe even more broadly, we know that sometimes referring to the gauge group is not necessarily a good idea. what if we don't have a Lagrangian description, or even if we have it, oftentimes it's not invariant under dualities. So if we rephrase the problem in terms of global one-form symmetries, we have, I think, a better description. And for instance, it can also be extended to cases where a Lagrangian description is not available. So it's not immediately obvious what it would mean to talk about, say, the global form of the gauge group, but we can still talk about global one-form symmetries, what happens if we gauge them, and all sorts of other considerations. And then there is another sort of step, which is useful to take sort of in perspective, and that is to go even one dimension higher. So I would like to convince you that symmetries are a topological sector, and not only that, like many interesting physical properties are captured by a TQFT that lives in one dimension higher. And in particular, what I would like to discuss today is that there is something that we might call the Symmetry TFT of our QFT that we want to study. And this gadget encodes two crucial aspects of the global symmetries at hand. It encodes the Toft anomalies for global symmetries, either ordinary or generalized, and also encodes this other aspect I mentioned in the previous slides, namely that sometimes there are choices that had to be made on which is the precise form of the global symmetry, one-form symmetry, say in gauge theory. And the purpose of the Symmetry TFT is to capture them both. And as it's sort of clear from the formalism, the notion of a Symmetry TFT doesn't rely on a weakly coupled description, so it's quite flexible. It can be applied in either if we have it or if we don't have this description.
One question.
Mm-hmm.
Where does the +1 come from? Why is it 1?
Yeah, this is something I will discuss a little later. So we'll probably hopefully answer your question. Otherwise, feel free from that. Okay, and then the final bit of the introduction is essentially, that was an introduction trying to convince you that this Symmetry TFT is an object that deserves interest. And now the second half of the title, string theory, where does that come from? And here the idea is that string theory is a powerful framework to realize a vast number of quantum field theories, and some of them admit Lagrangian descriptions, some of them don't. And in a sense, the key idea is that we're changing the paradigm. We're not talking about fields and Lagrangians. We're rather saying, let's put string theory in a given background, and it's the data of the background that defines the theory QFT. So I don't know what kind of geometry, if there are branes, and all sorts of things like that. So a natural question in this context is there a way of systematically extracting this gadget, the Symmetry TFT, that knows about the QFT, directly from the string theory setup, from the geometry? And in this talk, I will address an example, an important example, and namely field theories that are engineered by M-theory in singular spaces. So in particular, in this class of examples, there are no branes in the setup. And what we will see is that it is indeed possible to achieve this goal, to learn about the Symmetry TFT directly from the geometry. And roughly speaking, the idea is to take the topological couplings of 11D supergravity and perform a reduction, in quotation, because being topological terms, maybe it's not entirely obvious what that would mean. And there is one caveat that we encounter, and namely that in the game, we will see it's natural to have discrete global symmetries. And those, furthermore, are associated to torsion phenomena in the geometry. So we need a language that can sort of marry, if you wish, our understanding of the couplings in 11 dimensions with the torsion in space-time. And what we found useful to use to this end is the formalism of differential technology. So that will be the language that we use. Okay, so this was an introduction and motivation, hopefully giving you some framework of like why these sort of problems are interesting. And now we can switch gears and describe a little better, for instance, why D+1, what exactly this TFT is. And then I will turn to the main point, which is how do we get it from M theory? Okay. I think, at least for me, the way that in which I understand better why it's a useful idea to go to one dimension higher is to think about the way we usually think of Toff's anomalies. As you probably are all familiar with, the idea is to take a theory that has a global symmetry, couple it to a non-dynamical background. Here, quite schematically, I'm calling it A. It could be a principal G-bounded with connection, or it could be something a little more exotic. And the main idea is that if we perform a gauge transformation of the background field, the partition function is not invariant. And this cannot be cured by simply adding suitable local counter terms. And the other observation that has been made by several people and sort of formalized a little more precisely by the work of Dye and Fried is that there is a different but equivalent way of thinking about the problem in which we do the following. So essentially, our problem is that we have our physical space-time, but the partition function is not gauge invariant. What we can do in suitable circumstances is extend our space-time and consider it to be the boundary of a space in one dimension higher. And there are some technical conditions that have to be satisfied. For instance, if we have a spin structure that should extend, our connection, our background field A should also extend to what I'm calling A hat. So I'm using this compact notation to denote the fact that not only is space-time the boundary of an auxiliary D+1 manifold, but the structures in D dimensions also extend in a correct way. And now that we have this auxiliary object, the idea is, okay, Z in D dimensions is not gauge invariant. Let's cure that gauge non-invariance with a D+1 dimensional field theory that only depends on the background gauge fields. So this is this gadget I'm calling A, usually referred to as the anomaly theory. And its partition function is just a phase. And its purpose in life is precisely to reabsorb the non-gauge invariance of the physical theory. So now we find ourselves in a slightly different situation. Everything is gauge invariant, which sounds like good news, but the new improved partition function seems to depend on spurious data, this extension to one dimension higher. That's something we probably don't want to, depending on the context. Sometimes in condensed matter, the bulk is physical, and we're perfectly happy with this picture. But usually in high energies, we think of this D+1 space as auxiliary. But now we also have.
Sorry.
Sure.
It's only valid for a gauge field. Like if you have two forms, is the picture the same?
It's pretty much the same. The notion of gauge field changes. It's usually an element in cohomology with coefficients in the. Say if you have a Zn two-form symmetry, you would consider a background field which is a cohomology class with coefficients in Cn. And the
extension to D+1 works.
I don't know if it's been, I don't think it is a sort of a theorem, but I think it's an observation that has been made across many, many different examples. And it is believed to be a general picture on how to think of models. And now the idea, if you wish, so as I mentioned, now everything is gauge invariant, but sure. Yes.
Is there any example in which there is an anomaly, but it's not possible to cure it by this extension to the bulk?
If I'm not mistaken, I think in the work of Kapustin and collaborators, maybe examples of this sort have appeared. So in that sense, those seem to challenge this picture. That's true. I'm not quite sure what's the current understanding of those examples in this framework. It's still true, though, I would say that there are many, many physically interesting setups in which this picture applies that we can use. And indeed, so now we find ourselves in a situation where gauge invariance is not an issue anymore, but we have spurious data. But then there is also a natural way of measuring this dependence. If we were to choose a different extension, like the blue versus the red, then we can just glue them together with a flip of orientation along their common boundary, and we will end up with a closed T+1 dimensional manifold. And now the purpose in life of the anomaly theory is that it is also a gadget that we can evaluate on this closed manifold, and the partition function on that closed manifold measures, if you wish, the 't anomaly. If we want, say, the anomaly to be 0, to not be there, this curly A evaluated on closed manifolds should be 1, should be trivial. So now it measures for us the anomalies. And all of this seems probably a little abstract. In a sense, it is, and that's one of the advantages. But let me establish for you, I will not be super precise mathematically, but some intuition on something that we are probably more familiar with. Let's say we consider a standard, a free chiral fermion in some d dimensions, d being even clearly. Then we know that a very convenient way of thinking about the 't anomalies of these objects is in terms of its anomaly polynomial that satisfies the famous descent relations. So during descent, we go from this characteristic class in b+2 dimensions. We go down one step, we find the Chern-Simons term, the thing I'm denoting I0. And then if we go down further, that's essentially the known invariance of the partition function coupled to the background field. So we see that, at least schematically, we can think of the anomaly theory as the intermediate step. That's the Chern-Simons step of descent. And again, not super precisely, we can think of the Lagrangian of this anomaly theory as being precisely the I0 form. Now, this is not entirely precise, but luckily, Dai and Fried have found out what is the precise formulation of this phenomenon. Instead of thinking of this Chern-Simons action, which is more of a physical picture of what's going on, the formal statement is that the thing we should put there is the so-called eta invariant. It's an object that appears in the APS index theorem. And crucially, what these authors demonstrated is that the exponentiated eta invariant satisfies nice gluing properties. When I was playing this game earlier of comparing the blue and the red, gluing that together, I had to use that the anomaly theory is a TFT. So it behaves nice when I cut manifolds and I glue them together, I flip orientations. Those are all non-trivial properties, but the exponentiated eta invariance does indeed satisfy them. Okay, so this was essentially trying to convince you that if you think of an anomaly theory in b+1 dimension, you can recover more familiar anomalies, but all sorts of other phenomena as well. That's right. I believe that in that situation, this formalism, for instance, I think can be used to capture the SU2 Whitney anomaly, for example, if I'm not mistaken. So there are, yeah, clearly the interpretation would be slightly different, but definitely the formalism applies. Okay, and now to sort of like, because ultimately we would like to discuss how these objects are related to string theory. So let me connect to a familiar example in the framework of holography. So essentially what I would like to discuss now is that this anomaly theory, we can think about it as a purely field theoretic auxiliary object, but actually it also appears very naturally in many holographic examples that we know and love. So for instance, let's take 4D superintegers in ADS5 times S5. If we look at the field theory, it has a 't anomaly for its SU4R symmetry. It's just essentially the third Chern class. And therefore, the expectation from the general consideration is that the anomaly theory should be, at least roughly speaking, the Chern-Simons form for this characteristic class. And indeed, the low energy effective action of type 2b on S5 does contain a Chern-Simons coupling for the SU4H fields. So, of course, the 5-dimensional supergravity is far from being a TFT. It has all sorts of dynamical degrees of freedom, but within itself, so to say, contains some topological sectors. One of them being this 5-feature Simon's form, whose application to holography was already pointed out in earlier work by Witten and also other authors. So that's to say that we essentially what we would like to do is reverse the logic. Like, can we use supergravity, and in particular, the topological couplings in supergravity, to learn about the anomalies of the field theory? And I think it's good to remain in this concrete example of n equals 4 or a is 5 times s5 to try to combine the two features that I mentioned in the introduction. So one was how can we describe Toft anomalies in general? And then there was this other phenomenon of, say, of the gauge theories that have different spectra of line operators. And we will see that in this example of holography, we actually see both phenomena appearing at the same time. So in my mind, it's a sort of a nice example of what a symmetry TFT is and how it appears in string theory. So what am I referring to more precisely? I'm referring to the fact that among the various couplings that we encounter in the 5D supergravity that arises from type 2B on the 5 sphere, there is this coupling which involves these B2 and C2 two forms. Those are just U1 gauge fields in 5D, and they're literally the reduction of their 10-dimensional counterparts on the 5 sphere. And this term, this kind of action, this topological action, which is first order, is actually ubiquitous, and it usually goes under the name of BF theory. And what actually happens is that while it is written in terms of continuous fields, with B2 and C2, what it's actually describing in 5 dimensions is a discrete gauge theory. And to be more precise, this is a discrete gauge theory of two distinct two-form gauge fields. And they are both Zn gauge fields. And if you wish, a sort of a quick and dirty way to see why that's the case is that B2 acts as a Lagrange multiplier for n times C2 and the other way around. So roughly speaking, each field forces the holonomies of the other to lie in an nth root of unity. Why is this coupling interesting from the point of view of holography and in relation to the other things I mentioned earlier? Well, one of the important features of this coupling is that it is first order in derivatives. In holography, usually we impose Dirichlet boundary conditions for the supergravity fields to set up the holographic dictionary. Unfortunately, here we just cannot impose Dirichlet boundary conditions simultaneously on both B2 and C2. That would be inconsistent. We have to make a choice.
You cut down the time Lagrangian, like you ignore the terms.
Thanks for the question. The rationale here is that we're looking at what happens at the conformal boundary, so at very in the deep IR, if you wish. And by derivative counting, this term is argued to be the dominant term, precisely because it has only one derivative. Indeed, and that's why the analysis simplifies, even though it is also possible to combine the effects of the kinetic term and the BF term, in which case one would end up describing what's usually referred to as the singleton theory. But I will not be discussing that. That follows. Okay, so now we are faced with in a sense, it looks as if to make sense of holography, we have to make a choice. We choose B2 or C2 or maybe some combination. And that at first might be weird because we expect to have a single theory on one side and a single gauge theory on the other. But that's actually very natural because on the other side, on the field theory side, to be precise, all we know is that the gauge algebra is SUN. But what about the global form of the gauge group? And these two things turn out to be related. Indeed, say for example that we choose the Dirichlet boundary conditions for B2 and just free boundary conditions for C2. In that case, what happens is that a fundamental string in the bulk of ADS5 can end on its boundary and give us what is effectively a Wilson line in the theory. So if the theory has Wilson lines, it means that it's the SUN theory and has an electric one-form symmetry. Conversely, we could reverse the roles of the fields. This time it would be the D1 ending on space-time, giving us a 't line corresponding to a magnetic symmetry. And we can even do something more interesting. Let's say that n factorizes as the product of two integers in a non-trivial way. Then we can, we sort of like hand-wavingly say that we choose partially Dirichlet boundary conditions for both fields in a way that it's still consistent. And if one analyzes this situation, what comes out is that we actually now have both an electric and a magnetic one-form symmetries simultaneously with smaller ranks. As you can see, they're no longer the big N, but the smaller n and n prime. And another interesting phenomenon of this choice of global structure of the spectrum of line operators is that now these two factors have a mixed 't Hooft anomaly. And how do we see this from the point of view of the TFT? Well, in a sense, it's the BF term itself. So the purpose in life of the B2 wedge DC2 term is twofold. By a choice of boundary condition, it tells us what global one-form symmetry we are choosing, or if you prefer, what spectrum of line operators we are choosing. Once the choice is made, sometimes, like in this example, there is a residual 't Hooft anomaly, and that's encoded in the very same topological coupling. In that sense, this example, to me, it's quite paradigmatic of what the general picture about the symmetry TFTs is. And namely that, in general, the symmetry TFT is supposed to contain, roughly speaking, two pieces. Here, I'm not being super precise. We definitely want the anomaly theory, but sometimes we need more. We need the analog of these BF terms that allow us to choose which form of global, say, one-form symmetry, for instance, we have in the theory. And here, a note on terminology, the anomaly theory is usually understood to be an invertible TFT. So that's a technical property that it should satisfy. And these BF theories, for instance, generically are not invertible. So that's why we prefer to use the terminology symmetry TFT to try to convey the idea that these topological theories know about both phenomena, our beloved 't Hooft anomalies, and also this BF kind of effect about choosing different forms of their global symmetry.
So are you saying that like choosing different boundary conditions on the type of the string theory and radius times tensor 5, you would describe different dual for the H theories, including on the tree rings? Is that the claim?
There are like two ways to think about it. If we think of the, if we only focus on the BF term, using this argument about the D by R, then indeed boundary conditions would correspond to different version of the SUN H theory. There is also another picture which makes maybe a bit more contact with the word volume of the brains, and namely to reintroduce the kinetic term. Well, they're always there to consider them, let's say. And then what the combination of BF and kinetic terms is effectively doing is describing the center of mass mode that decouples from the dynamics. So in that situation, effectively what happens is that, if you wish, the total partition function of the system splits as a sum of factorized terms, which are the partition function of the singleton contracted with the partition functions of all these various cousins of the SUN theory. So that's an interesting, that's a possible point of view. But the point of view that I'm advocating here is to truly decouple the center of mass mode, which is usually what we do. And that's okay, but we have to keep in mind that we have to make a choice if we want to do so. And that's where this business of boundary conditions come into play.
Different choices of factorization.
Well, if you wish, it's like selecting different terms. Like the singleton field doesn't have a single partition function, it has like a Z beta vector, contracting with another Z beta vectors of different versions of SUN theory. And effectively, we're selecting a component of this theory. It's also, I think, what's sometimes referred to as a relative field theory. It's a theory that doesn't really have a single partition function, but rather a vector of partition functions. And what we usually want to do is to select one of the components, and that's what this TF theory is.
So, sorry, the Bonetti with the UN theory. So what the theory you're talking about is somehow something you can describe as coming from the UN theory through factorization of the median term, but it's not truly the theory that is built to be. It's
Well,
artificial to factorize.
Let me say, I would say that we usually think of ADS5 times S5 as being dual to SUN as opposed to UN, because the U1 doesn't gravitate in the bulk. Like you can see it if you want from holography, but then it's stuck at the boundary. It's this singleton mode. So I would say it's there. So in a sense, one could say that ADS5 times S5 is dual to UN. But if we adopt this point of view, then we should also keep in mind that the partition function of this UN theory, it's not just a simple product, center of mass times interacting, but rather a sum of such terms. And those terms correspond to the partition functions of the, say, SUN theory, PSUN theory, and so on and so forth. It's a TFT whose, well, I'm not an expert in category theory, but roughly speaking, whenever like a TFT associates different objects depending on the codimension, the idea is that all of them should be invertible in the appropriate sense. For instance, a practical criterion is if you evaluate it on a codimension 1 space, it should give you a Hilbert space, and that should be one-dimensional. If it happens to be a higher dimension, then, for instance, you know it's not Hilbert. And this is what happens to BF theories. Essentially, their Hilbert spaces would be more than one-dimensional, so they're not really anomaly theories, strictly speaking. And yeah, here I would just like to briefly conclude with this picture, which I find kind of amusing, that there is a notion of what it means to choose boundary conditions. And in a sense, pictorially, we can think about it this way. So on this side, there is the QFT we would like to study in D dimensions. Then, as I told you, we should extend it to this symmetry TFT. So here, for instance, you will find your Chern-Simons term, your BF terms. But then say you want to study a specific gauge theory with a specific choice of gauge group. Then what you can do is to introduce a gapped interface between the non-invertible symmetry TFT and the invertible anomaly theory. And the purpose in life of this row is to describe in a slightly more general framework what concretely is, for instance, say, choose boundary conditions for B2 as opposed to C2. So this is a more sort of a bit more pictorial and abstract, but I think that it's nice to keep in mind because it's more general. Like maybe there are other examples that one might contemplate in which it's not as simple as choosing boundary conditions for a BF theory, but this picture should apply. Okay, so this was about hopefully convincing you that this point of view of going one dimension higher and focusing on a TFT is useful and includes a lot of different physical properties. So now comes the challenge. How are we going to extract this TFT if we realize our QFTs using string theory or M theory? Of course, there are many different constructions in string theory, M theory that we can consider. So let's focus on a specific class. Let's say that we want to consider M theory on singular geometries. So in particular, there are no branes. And to be a little more precise, let's focus on two concrete examples to keep in mind. One is just M theory on an ADE singularity, that's C2 mod gamma, where gamma is a subgroup, ADE subgroup of SC2. And we know that this gives us in the IR, that's the same as just 7-dimensional super Yang-Mills with gauge algebra of ADE type corresponding to gamma. And a much more interesting class of examples comes if we consider instead M theory on a Calabi-Yau threefold. Because in that case, if this threefold is a cone, we get a five-dimensional SCFT. And here, just to keep in mind, there is another famous construction involving Calabi-Yau threefold cones, namely when you put D3 branes on top, but that's a different game. That's a 2B game. Here, I will be focusing on the sort of M theory version where there are no branes, it's just pure geometry. And what turns out to be the case is that depending on the geometry of these threefolds, sometimes the 5D CFT admits a mass deformation that gives us in the IR a non-abelian gauge theory. So in that situation, it's qualitatively similar to the example of 7D super Yang-Mills. But sometimes that's not the case. And those cases are extremely interesting, precisely because they elude this more familiar Lagrangian description. So our goal is to develop tools that are systematic and geometric, and therefore they don't really rely on whether or not a description in terms of a non-abelian gauge theory is available. And just as a side note, for the rest of the talk, I'm going to describe geometric engineering. It's natural to wonder, can we play similar games with branes? And the answer is affirmative. And in a sense, for instance, with M5 branes and D3 branes, my collaborators and I have developed a few systematic tools that give you both anomalies and BF theories in other constructions. So in a sense, it's also a symmetry TFT in the terminology of this talk. And as I will comment briefly at the very end, I think it would be interesting to try and combine this brain constructions with the approach that we will see in the rest of the talk. But that's not going to be discussed today. Okay, so how should we tackle this problem? Okay, what we're given is essentially a singularity that looks like a cone. Say we want to engineer, for instance, a CFT. And it's linked by a compact space that I'm calling L, being the link. So if you want to keep in mind concrete examples, if we have C2 mod gamma, the link is literally an S3 mod gamma, something like a lens space for the A series. If we consider a Calabi-Yau cone, the link is nothing but the familiar five-dimensional Sasaki-Einstein manifold that we see in Calabi-Yau cones. And here the idea is that since we are dealing with topological quantities, at least heuristically, what we can imagine is to trade the cone, which is the actual geometry, for like this cigar-like structure. And the intuition being that this is a smooth deformation and topological quantities shouldn't depend on it. And then, as you can see, we can even imagine a limit in which the size of the cigar collapses, and we're literally left with something that lives in one dimension high. So this would be a heuristic way of arguing that what we should do is to start with our 11-dimensional supergravity and reduce it on the link, like a la Kaluza line. Because then what we get has precisely the correct dimensionality for being a candidate symmetry TFT for the QFT that we want to study. So the QFT would live at this marked point. Well, clearly it's not a point. There are transverse directions that I'm suppressing. And its symmetry TFT would live in this line that ends on the point, in accordance with this picture of it being an extension whose boundary is spaced on.
So I did not get when the CDR is important for the argument you just give, where you cannot do it just in the case of the cone, where yes, the direction of the cone.
Oh, no, it's just a technical simplification in that the asymptotics of the cone is just a simple cylinder, it's just a direct product. Whereas if we look at the metric, at least, it's like a cone. So like the size of L would depend on the radius. But yeah, indeed, there is nothing maybe too deep here. We shouldn't care about the size if we're looking at topology.
It's just about the rock.
That's all.
Do you add a half line or a line?
In this case, it looks like a half line, and I think that's what we want because we want to picture a D+1 space that actually ends and has our space-time as a boundary. So yeah, it would be ending like that.
So it's in your matrix, this TFT plus the boundary condition?
No, what we will be deriving is, if you wish, the Lagrangian of the TFT itself. Then one, for instance, could perform a detailed study of what kind of boundary conditions are allowed. But computationally, this picture is just to justify the claim that if you want the Lagrangian of the symmetry TFT, you can get it by dimensional reduction on the link. If you wish, you can also take this perspective as a working assumption, and it would be ultimately be justified by the fact that the outcome of this procedure matches with known results. Okay, 15, okay. Okay, now I would like to, okay, so before maybe jumping in the last set of slides, which maybe are likely more technical, let me tell you what I would like to describe for you. So I tried to convince you that there are two pieces of this story, the BF game and the anomaly terms. And our task now is twofold. We would like to recover them both from M theory. And I will say something briefly about the BF terms, but I will not be able to explain it in its full glory. And then I would like to say something about the anomaly terms. So how do we go ahead and argue that there are BF terms in the symmetry TFT? Or at least, how can we detect if they're present or not? One way to do so is to rely on a picture which is based essentially on the work of Friedmoor and Segal, or on non-commuting fluxes in generalized Maxwell theory. And namely, it stems from the observation that in general, if we take M theory and we consider the holonomies of the 3 form and the 6 form as quantum operators, those actually don't really commute, but rather they satisfy a commutation relation of, as shown there. And if you exchange them, you pick up a phase, and that phase is given by a linking pairing. So what's happening here is that the cycles that I use, the 3 cycle that I use for C3 and the 6 cycle that I use for its dual C6 are supposed to be torsional. And therefore, there is a well-defined notion of a linking pairing between them in the ambient space. And here, I'm referring to a Hamiltonian picture. So I'm thinking of one direction being selected. In the previous picture was the radial direction, if you wish. And therefore, we're effectively down to a 10-dimensional space-time that accommodates these torsional 3 and 6 cycles. And in this ambient space, these two objects can have what's usually referred to as the linking pairing. And intuitively, at least in my mind, this is just the analog of the familiar intersection pairing between cycles in the realm of torsion. One has to keep in mind, though, that while the intersection of cycles in the usual sense is an integer, the linking pairing instead is a phase, or an R mod Z1, if you prefer. So this is a basic relation that describes the failure of commutativity of fluxes, if you wish, in M theory.
So here you just use canonical translation of the.
Yeah, exactly. Yeah, that's right. Indeed, and in this relation, for the time being, I'm neglecting the effect of the Chern-Simons coupling of M theory. And that guy will reappear and will be the main actor in the second part when we focus on the anomalies. And okay, so this is the picture in the parent theory upstairs. And now I told you that what we should do is do a dimensional reduction on the link geometry. That, say, for example, could be a length space for concreteness. And this can be done intuitively, just sort of, if you wish, factorizing everything. So let's take our space-time to be external times the length space. And then we have a 3 cycle and a 6 cycle. And let me construct them using the only torsional 1 cycle that I have in my length space. There is only one generated. Let me call it early C1. And now it's a fact in this game of linking pairings that the linking pairing of these factorized cycles factorizes in a nice way. One factor is an ordinary intersection of this things I'm calling sigma 2 and sigma 5. These live in external space-time, and their intersection is just an integer. And then we're left with another linking pairing inside our length space with this quantity L inside L3 of curly C1 with itself. And this is just a geometric quantity. It's a property of the geometry of the length space, and it's well known to be equal to 1 over n mod 1. So we can plug that in. And then we realize after this dimensional reduction that in the lower D theory, now we have a different set of non-commuting operators satisfying these sort of canonical looking commutation relations. But now, as you can see, the phase factor is expressed as an ordinary intersection pairing over n. And this is actually the hallmark of a BF theory. It's something I haven't showed you when I reviewed BF theories, but one can show that it's a general feature that if you perform canonical quantization of that kind of theory, you end up with this sort of operators precisely with this phase factor, which is the intersection over n. And therefore, this is an indirect argument in favor of the statement that the symmetry TFT of this example should contain this coupling. Is this a sensible thing from a field theory perspective? Actually, it's very well, because I told you that we expect to realize a 7D gauge theory with gauge algebra SUN. But what is, again, the global form of the gauge group? And this BF coupling is precisely there to tell us that we have the freedom of choosing the global form of the gauge group. And that's the same as choosing boundary conditions for B2 or C5. In the previous example, it was B2 and C2 because the gauge theory was 4-dimensional. Now it's 7-dimensional. This is a very close cousin. And as you can see, one can play a very, very similar game and encode both the electric and the magnetic versions and all sorts of ionic versions. So that's nice. So it means that these ideas of reducing topological couplings, or if you wish, reducing canonical commutation relations, yields good results. But this is somehow maybe a little, it's definitely not the end of the story. And one might argue that the most interesting part is actually the anomaly terms, because there are mixed anomalies of various kinds, and we would like to study them. So how do we tackle that problem? That problem can be tackled in a way that is much more reminiscent of a Karuza-Klein reduction. So essentially what I would like to propose to you is that you can literally take the couplings of 11D supergravity, reduce them on the linked geometry, and get the answer. There is only one caveat, though, that in the process, you have to, in quotation if you wish, include external gauge fields that correspond to torsion cycles in your internal space. That's motivated by the fact that it's precisely the torsion that gives you the discrete symmetries. So for instance, in 5D models, there is a very general recipe for finding what the one-form symmetry is, this object I'm calling gamma 1. It's not super important to review how that works and why that's the case, but the take-home message is that these are discrete symmetries that we would like to study. And therefore, we have to be able to do a KK expansion on torsion cycles. Now, how can we do that? Clearly, a torsion cycle will not have a harmonic form representatives in the usual sense. Now, there are approaches that use non-closed form to do this, and they have been successfully applied in some examples. But what we prefer to do is to change gears and use something a little more sophisticated than differential forms, and namely differential cohomology, because it's true that it's a little bit more abstract, but in my opinion, it's a bit more mathematically sound, and it's also more flexible because, at least in principle, it can be applied in more systematic ways, whereas these other approaches seem to be harder to generalize in a systematic way. So now, of course, the natural question is, what exactly is differential cohomology? And that would require a long discussion that we don't really have time.
Can you argue that, I mean, those fields would not be there if you were actually doing the dimensional, the reduction, the second reduction of supergravity. And you argue that they would be there in n terms. They have to do with winding or something like that.
Well, in this approach with, say, the non-closed form, for instance, they are related. One way to see the emergence, for instance, of discrete Zn gauge field is by a Stukelberg mechanism. So effectively, you expand your forms in, say, C3 of M theory into non-closed forms and D of them. And if you follow through the Lagrangian, you see that these two different external fields interact in a Stukelberg coupling. And while they are both continuous, because of the Stukelberg mechanism, at the end, they're effectively describing for you a discrete gauge field. So that's one possible way to think about what's happening. Those are like, at least in some examples, you can think of them as the remnant of U1s that were broken by Stukelberg mechanisms. But I would argue that the advantage of using the formalism I'm advocating is that you don't need to rely on this Stukelberg picture. You can just see that it's like the translation of the usual statement that, say, if you have a harmonic form, you expand C3 on it and you get a continuous gauge field. In this formalism, you can see that if you have a torsion cohomology class, you still expand G4 on it, and in exactly the same way, you get an external field. So maybe it doesn't give you immediately a physical picture of why it's there, but I think it's nice in that it's more general, and it doesn't rely necessarily on this Stukelberg mechanism too.
So you don't need a theory, you can do it just classically to the roads.
Well, the only caveat we see is that there is an important higher derivative correction, the famous C3x8 term, that has to be there for consistency. Yeah, but
extended objective.
Can you deal with C3x8 in a single fashion?
In
With C3x8, can you deal with in similar fashion?
you mean if you can see it in differential cohomology? Yeah, essentially, like all our favorite characteristic classes, like the Pointryagin and all, they all admit a natural refinement in differential cohomology, and then you can use that. Okay, so in the interest of time, essentially, what are the main messages of this differential cohomology business? Luckily, everything works formally as if we're doing differential form computation. So for instance, the analog of a wedge product is usually denoted by a star. It's defined in a different way, but it has very similar properties. For instance, the famous graded commutativity. I would say that maybe the most important new ingredient in the game of differential cohomology is that, if you wish, like there is a notion of integrating that it's twofold. With forms, the only thing you can really do is take a top form in your manifold, integrate it, and get a number. With differential cohomology classes, you can do two different things. You can still pick a top dimensional class and still get a number, which is actually integer because of flux quantization effective. But you can also take a class that has a degree which is the dimension of your space-time plus 1. So naively, that would have too many legs, so to say. But in this formalism, it makes sense to integrate it. And in this case, you would get a phase, or something that's usually referred to as a secondary invariant. And this will be the key ingredient. So, for example, one application of all this notation and formalism is the following. Let's say we are in 3 dimensions, and we're given an ordinary gauge field. In this notation, this guy corresponds to this A check that lives in H upper 2 check. It's a degree 2 cohomology, differential cohomology class. In physics, we would just call it A usually. Then what you can do is to take the product of 2 of these. This is a degree 4 object. You integrate it on 3D space-time, and you get a phase. And what that phase is actually nothing but the familiar Chern-Simons invariant that normally we would write locally as A. So the point of this formalism is that it makes it possible to treat this Chern-Simons-like invariance in a rigorous way without having to resort to, say, a local description or a description in terms of differential forms. And
it's restricted to abelian H fields.
Yes, that's correct. This is an abelian example. And now we can see, again, the details are not super important, but I hope I'll be able to give you the message. So how would we, in a normal situation, what would we do? We would say, okay, let's pick a basis of cohomology classes in internal space and expand G4 on it. So this would be the first term. So the V's, for me, are generators of the non-torsion part of cohomology. These are, if you wish, the harmonic forms that we know and love and we are more familiar with. Now, with this formalism, we can have a second set of terms. Let's include all the generators of cohomology, including the torsional ones, the T's. In this formalism, they all admit a differential refinement, so they get a little check on top. And we can do formally exactly the same thing, as you can see. Now we do a KK expansion. There is an external gauge field that I'm calling B, and an internal form, in quotation, that I'm calling T check. And the interpretation is very similar. We know that the F's are external continuous symmetries. What turns out to be the case is that the B's are external discrete gauge fields. So as you can see, this formalism is very flexible and it kind of democratic. It treats torsion and non-torsion on very similar footing. And that's why I think it's quite nice. And now we can really do a KK expansion as we would do in general. Like we would say, let's pick the ansatz, let's put it in the action. This is like the differential cohomology version of the familiar 11D supergravity. Expand everything out and integrate in the internal space. Now, we're not dealing with forms anymore, but all these formal manipulations that we would do in a more traditional computation still hold. So the computation can be performed essentially in the same way. What do we get? Let's look at an example. Maybe let me skip this slide. I'll just say it in words. Let's imagine that G4 is given by the expression up there. So here I'm imagining a three-dimensional link, the length space we have encountered before. And I'm observing that among its cohomology classes, there is a trivial 0th order cohomology class. I'm calling it 1. And then there is a torsion class, which is the interesting one. And let's say, okay, I will expand G4 onto these classes. So gamma 4 is a purely external gauge field. It's continuous. B2 is an external discrete gauge field. Discrete because it's associated to a torsion class. If you plug this into G4Q and you collect things, you see that there is one term which is non-zero, namely where you take two copies of T's and you put them together. This is a degree 4 class, which you can integrate on your 3D link space to get a non-zero result. So what's happening is that these are external fields. So this is a term in the anomaly part of the symmetry TFT. It's a term in our Lagrangian that we're trying to find. And this quantity here, it's the 't Hooft anomaly coefficient for that term. And now we are given a very geometric prescription to compute it. Maybe it's hard, but it's very well defined. It's a transimulus invariant that you should compute on the three-dimensional link. And as you can see, it's purely geometric. The only thing you need to know is that there is a link that has a certain torsion cohomology class that has a certain differential refinement. And essentially what we were able to find in interesting classes of example is a way of computing this invariant. And here I won't really have time to tell you the details, but I can tell you the message. It's based on this equation here. So the thing we would like to study is a transimulus invariant that you compute purely in terms of the link geometry. That in general is a hard problem. One way to tackle it is to say, well, we can remember that the link is actually the boundary of a 4D space, which is the C2 mod gamma singularity that we started from. So let's resolve that singularity. We know we can do that, preserving supersymmetry. And then we have a smooth manifold. And the key idea, which is a non-trivial fact in mathematics that dates back to results of Gordon and Gilterland, is that if you're given this object I'm calling T2, this is a torsional class of the link, you can uplift it to a non-torsional two-cycle in the bulk. The thing I'm calling Big Z. Big Z is just a compact cycle in the 4-dimensional geometry. It's something we are more familiar with. And something in particular, it's amenable to take in ordinary intersection pairings, the object I'm calling Z.Z. So this is just, you have your resolved C2 mod gamma singularity. I give you a very specific linear combination Z of its resolution two cycles. And then you can go ahead and compute the intersection Z.Z using, for instance, the fact that the intersection pairing is the same as minus the Cartan matrix of the ADE singularity, which is a well-known fact about C2 mod gamma spaces. So the take-home message is that an apparently hard and abstract computation of the Chern-Simons invariant can be mapped to a much more familiar computation of compact cycles in a resolved Calabi-Yau space. And it is precisely thanks to this technical point that we were able to extend this to the Calabi-Yau threefold case, applying more or less the same recipe. And to give you an example, let's take our, for instance, the cone over YPQ. That's a famous Calabi-Yau cone. It is known what happens in field theory. This is a CFT that admits a deformation to SUP gauge theory with Chern-Simons at level Q. And it has a known discrete one-form symmetry. It would be this B2 that I was talking about. And it also has a continuous symmetry, which is like the instanton symmetry of this 5D gauge theory. So that's just an example that admits both discrete and continuous symmetries. And using this formalism of how to compute Chern-Simons invariants in terms of intersection numbers, we were able to reproduce two different mixed anomalies. Well, the first one is actually pure, is the discrete one-form symmetry Q anomaly. And the second part instead is mixed between the discrete and the continuous. And those were derived in field theory using entirely different arguments. And for us, it was very reassuring to see that geometry alone knows precisely about these coefficients. And then sort of like starting from this, we studied several other examples. Some of those don't have a Lagrangian description, so it's not so easy for him. It's not so clear how he would generalize, for instance, the arguments of these authors to tackle those. But from our geometric point of view, they're just another class of toric Calabi-Yaus. So it's pretty much the very same game. They can be treated all different. Okay, so I'll be brief. I hoped I was able to convince you that if you want to study the global symmetries of a d-dimensional QFT, you should look at a topological field theory in one dimension higher. And also that in the context of geometric engineering, on the one hand, it's an important question to construct with symmetry TFT. And on the other hand, we have made progress towards this question with this formalism of KK reducing along torsion cycles. There are many interesting directions that I think could be explored. So for instance, we can remain within geometric engineering in M theory. We could consider maybe a Calabi-Yau fourfold, that would be a 3D theory. Those can also have very interesting anomalies. Or what about elliptically fibered Calabi-Yaus? Then we could maybe apply M to F theory duality and try to learn about many interesting theories that are engineered by F theory in singular spaces. And also I would say, why not combine the torsion paradigm and the anomaly inflow paradigm in constructions that have branes, or in holography? That's also, I think, an interesting question. And another thing that I think might be conceivable is, we know, especially when there are branes, that sometimes the isometries give you global symmetries. For instance, the R symmetry is usually an isometry in holography. Can we include both torsional contributions and isometry contributions? I believe that should be possible, presumably using an equivariant version of differential cohomology, but that's it's just a guess. And finally, here I focused on for me, the generalized symmetry, they were all higher form symmetry, but they were still group-like and sort of simple in that regard. But we know that there's much more out there. For instance, there are higher group structures, and there are many examples in 5D SCFTs, for instance. Some of them then realized by M theory. So another natural question would be, is there a way to use this KK reduction with torsion to capture not only anomalies, but also higher group structures? So these are just a few examples of things that might be interesting to study. And I think I'll stop here.
Okay, so thank you for a very nice talk. Any question?
In the context of M theory and torus vibrations, discrete Zn, I think 0 form symmetries in this thing often arise from terminal singularities which cannot be perfectly resolved, at least not perfectly resolved algebraically for the planet. but you can only do a large flow of the target, the Flavian property, or do a non-Kerr small resolution. Can you apply the same technology to these dominant singularities, perhaps in a local model around the spaces when they're embedded in a complex sort of Flavian?
Thank you for the question. I think, well, we haven't looked into that precisely, but I believe that to be possible in principle. And the reason why is that I would say that the advantage of this point of view is that the actual object of interest is this bi-Dietrich sinus invariant. And then how you compute it, in a sense, is up to you. So using a resolution which is not of a more standard or nice type shouldn't be an obstacle in principle. It might be a technical obstacle in that performing this link, this connection between the sinus invariant and intersection theory might be more complicated to perform on a technical level. But I would say that those examples could be very interesting testing ground exactly of like how general this approach might be.
Okay. Any further questions? Anyone on Zoom? You can unmute yourselves and.
Have you considered like 2D on the area of two singularities?
No, that's also a very interesting natural thing to consider. In type 2B, there might be a slight technical issue in that it's essentially the self-duality of F5. But that, well, it seems to be probably more of a technical problem than a conceptual problem. So I would say that, yes, that should also be something that can be tackled with these methods.
The same as a way of describing the same or form describing adding another couple instrument. I don't know if the topological properties are also described.
No, indeed, that would be, it's something I would like to understand better, indeed, but it's quite promising. It could be a very useful formula.
I have a question. Can you hear me?
Yes.
Yes. So I was wondering, I mean, so this differential cohomology, it has sort of two advantages over, well, ordinary cohomology. It's the integrality and torsion, and what you need here is the sensitivity to torsion, right? That's what you're using, that you can do your reduction and somehow take into account the torsion.
Yes, that's
okay.
Right.
Okay, and then the torsion, somehow you showed us that it's related to this entire story by using these holonomy relations and saying, look, this is the same thing that we get in BF theory. Is that correct? So you had these relations of phi of T3, T whatever is equal, and they changed the order and there was a phase, and you said that's the torsion related phase, and we get the same types of relation in BF theory. Yeah, and I was wondering, so BF theory just deals with ordinary differential forms. So how does it know about torsion? How does torsion enter in that story?
Well, in a sense, I think in the example I was discussing, the torsional element was, roughly speaking, washed away in the process of dimensional reduction. We had torsion upstairs, where there was a torsion pairing of torsion cycles. But then everything was factorized and all the torsional elements were soaked up by the lens space. And what we ended up with downstairs was a commutation relation where the phase was written just in terms of non-torsional intersection pairings. Or maybe another way maybe of phrasing my answer would be, here I have been only considering torsion in the internal space. It's also very natural and probably very important to wonder what happens if I also allow my external spacetime to have torsion. And then I would agree that probably almost certainly a BF formalism might be quite not enough, because there could be more subtle phenomena that enter in the game. And I would say that situation, maybe it's not even clear to me that we should consider the differential refinement of ordinary cohomology. Maybe we should consider differential refinements of more sophisticated cohomology fields. So maybe in short, I would say that we got away without having to deal with all these problems because we made the simplifying assumption that there was no torsion in external space-time.
Okay, I see. Thank you.
Okay, so then,
Yeah,
okay.
I did not get if this differential technology are actual form associated to it that you can define, I guess, of a non-fixed degree, or it's just a formal set of rules that allow you to define what is the integral of a given element.
I think it can be sort of characterized by some abstract axioms. So in a sense, it becomes a set of rules, but they're also very concrete realizations. So for instance, one realization is in terms of Cheever-Simons characters, and those are quite physical. Essentially, they would tell you that
There is no form to make it, there is just a form.
well, the point in life, so to say, of these differential cohomology class is to contain all the gauge invariant information about a gauge field. So that part of that is holonomies, which are not really local in space-time, so to say. But then there is also the field strength, and that is a bona fide differential form. So I would say that roughly speaking, there is a differential form inside a differential cohomology class, very hand-wavingly. And what is nice about these objects is that they're a little abstract, but they know really about both local gauge invariant data about the gauge field, such as the field strength, and non-local gauge invariant data, such as holonomies. Yeah, I mean, it just like maybe a more formal statement would be that there is a whole set of, say, short exact sequences that tell you precisely what the relation is between differential cohomology elements and closed forms, or cohomology classes without differential refinement. So there is quite an amount of technology that one can use.
What's useful is to direct on the screen more written to the precise relation of the topological property in different dimensions.
Yeah, indeed. Like I would say, well, yeah, most of the time wherever you have a Chern-Simons action, especially in abelian Chern-Simons action, the proper way to formulate it is in this language. In the case of M-theory, there are sort of additional subtleties related to the 1/6 coefficient that make the story even a little more subtle. But I would agree. It's, this language, it might be unfamiliar, but in a sense, it's a very natural and very physical way of describing topological couplings of Chern-Simons form in all dimensions.
Okay, so then no further questions. Let's thank Federico.
And for